Can you hear me? Is it on? Well, I want you to know, for the 25 of you who are here, there's still 167, I think, students enrolled in this class, which, you know, and as I'm speaking to the ones who are actually here, good for you for coming. My bet is that in this room we have many of the top performers in the class, because attendance is half the battle. So I do appreciate you who do come. I just wanted to say that end of the semester. So I don't have a lot for today. I do want to go over the question of the day, and then I'm going to open the floor for questions. I actually brought all the slides from the semester, I think, with me. So if there's a specific question, we can go back and cover it. I can answer questions about the test. I can answer questions about going forward, what your next classes are, the CS major and the other majors at the university that are computationally related. So anyway, let's get underway. So don't forget the homework's due tonight. The usual 24-hour extra time for 75% credit is extended to Monday night at midnight because it's finals week, and I figure some people might be stuck. Question of the day 17, as I described, is a special edition, so it's essentially extra credit. I'll have that graded later today. I'll have your estimated grades Monday morning, because homework 2 is almost complete now, I think, and it's supposed to be complete by Sunday. Final exam is next Friday from 3 to 5. SDS people, I will have your proctor exam stuff set up, I hope, by the end of today. We just had a couple of kind of emergency things happen in the department, which are occupying a lot of time for me. So if I don't get to it tonight, I'll get to it on Monday morning. Okay, so how many of you did question of the day 17? Was it hard? Yeah, okay, well, this is a cool problem, right? This is the quintessential CS-like problem. So the question of the day asks you to take a set and return what's called a power set of that set. So it's got this, power set's got a cool name, but what it really is the set of all sets that are subsets of the original set. So if I give you a set 1, 2, 3, we know that there are subsets of that set, the set 1, the set 2, the set 3, the set 1, 2, the set 2, 3, the set 1, 3. The set 1, 2, 3 is also a subset of itself, and the empty set is a subset of any set. So if I have the set with 3 elements in it, we've just talked about how there are 6. Were there 6? 1, 2, 3, 4, 5, 6, 7. There are 8, obviously. There are 8 different sets in the power set of a set of 3 elements. So the first question you might ask when you're asked to do this is, how many sets are in the power set? And the answer is, for a set of n elements, there are 2 to the n sets in the power set. So let's talk about this. So this 2 to the n is the canonical exponential thing that we worry about. So one thing to think about, how fast is your power set function going to be? What's the runtime of your power set function? Anybody? Just take a guess. Exponential. Why is it exponential? Here you can't guess. Any idea? In the back? Okay, so close, right? I mean, if I'm going to generate as output the power set of a set, then I know that even just outputting the output will take exponentially time exponential in the size of the input. So remember, a program, from the very first day of class, we said a program takes an input, does some stuff, and produces an output. And the rate limiting step in these programs, when we talk about analysis of algorithms, it's all about sort of what's the rate limiting step. And we talk about how sorting has a log n rate limiting step in the computation step and so on. But in problems that generate exponential amounts of output, the inside rate limiting step almost doesn't matter. It's just printing out the output is going to take time exponentially more time than reading in the input. So in this case, we have a problem where the input size is something and the output size is exponentially larger. So it doesn't matter what the runtime is, because part of the problem-solving process is providing the output, and that's going to take exponential time. So your algorithm, you don't have to look for an efficient algorithm. You don't have to worry about is it n log n or n squared. It's going to be order 2 to the n, period. No question about it. So where does this come from in this relationship? Well, here's the way to think about it. To construct this power set, imagine a vector or a set of bits that are n bits long. So imagine you have a number that's n bits long. So for a power set of a set of three elements, it's 3 bits long. How many different bit combinations do you have that are 3 bits long? Every bit could be 0 or 1. And when you think about it, you have 2 to the n combinations. So for a 3-bit sequence, you have 8 different combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Just write them out. There's 8 of them. 2 to the third is 8. So for an n-bit string, you have 2 to the n different n-bit strings available to you. The 2 comes from the different elements that are in that vector, 0 and 1. There's 2 things in the alphabet. The n comes from the length of the vector. That's really the only math you need in computer science. You need to understand exponents in base 2. So for a bit vector of n bits, there are 2 to the n different incarnations of that bit vector. Now imagine that each pattern represents an element of the power set. So each of these 2 to the n different bit set patterns corresponds to one of the sets in the answer. So the answer is a set of sets, and each one of those sets corresponds to one of these 2-bit patterns. How? Well, if the bit in location x is 1, then that means that the element corresponding to x in the original set will be in this subset, in this element of the power set. If the bit is 0, then it's not. So if I have the set, ABC, and I have the bit pattern 1, 0, 1, that corresponds to the set AC, which is an element of the power set. For the bit pattern 1, 1, 1, that's the set ABC. For the bit pattern 0, 0, 0, that's the empty set, which is in every power set. The empty set is a subset of everything. Does everybody get this? So here's my solution. It's a recursive solution. The general idea here is I'm going to step down every element of the set that's input to me. And for each element of the set, I'm going to imagine 2 paths forward. In one path, I include that element of the set in all of the sets I've got in my power set that I'm constructing. In the other alternate path, I'm not going to include it. So the whole idea of this recursive function here is if the length of the set is 0, meaning it's the empty set, then I'm going to return the list containing the empty set. So what is the power set of the empty set? It's the empty set. Right? Then I'm going to consider the first element in this set. So I'm going to remove an element from the set. And I'm going to construct this new list, which is the power set of the remaining elements of the set. So mu is the power set of the set S less the element I just removed. Because I just removed an element. Right here, I got rid of an element from the set. So now S has one less element. Mu is the power set of that shorter set. And then I'm going to return 2 things. I'm going to return a list which is this power set I got back. None of those elements of the power set contain this element. And I'm going to build a comprehension here over that set nu. So nu appears twice. For every subset in this list, I'm going to take that subset and add the element I just removed from S. So 2 paths forward. The path without the element I removed and the path with the element I removed, I'm going to concatenate those strings together. So let's think about it. Let's say I have a set of two elements, A and B. So S is the set of two elements, its length is not 0. So I'm going to pop an element off that set, and that element will be A. So now I compute the power set of the singleton set B. So just set this aside, we'll come back up here. The set is not length 0. I'm going to pop an element out of that set, which is now B. So this is my element, will be B. Power set of S now, S is one less element, so it's the empty set. And that'll be U. Well, what is the power set of the empty set? Well, it's simply a singleton list with the empty set in it. And to that list, I'm going to have the empty set plus every subset in U, which is only the empty set, with the element B added to it. So at the end, I will have the empty set and the singleton set B. That'll be the value of mu that I return from the spanning call. And so I now have U, which is the empty set plus the single set B, plus for every element in that I'm going to add A. So I will have the set AB and the set A, just a singleton set A. So I now have 4 elements in the thing I return. I have the set A, the set B, the empty set, and the set AB. And so this unpacks everything all the way down to the empty set, puts the empty set in the power set, and then builds the power set on the way out of the recursion by either incorporating the element I had removed or leaving it out of those growing sets. And then as I recursively exit, each of those sets will then incorporate other elements. Does everybody get the general idea here? This is a hard problem. I didn't give it to you because it was easy. But it is kind of the combination of a lot of the elegant ideas that I hope you learn this semester. The notion of using recursion to pack and unpack stuff, sort of take it apart and then rebuild it differently. The idea of runtime, in this case being exponential time because of the very nature of the output. Right? We can ask ourselves, can I analyze this algorithm and come up with the fact that it's exponential runtime? And the answer is, sure I can. What is the cost of every step in this path? Well, let's do it this way. How many recursive calls will I have? For an n element set, how many times will I recursively call myself? Every time that set gets shorter by 1, so you can imagine a tree of depth n, where there are 2 paths through every tree, the path that includes the element, the path that does not include the element. So I have a tree now with branching factor 2 and depth n. How many nodes are in that tree? Well, that's the definition of 2 to the n. So we have an argument for the runtime of this algorithm being exponential time, which we had already argued because of the size of the output. Questions? Okay. Finally, there was a question on Piazza. We're returning a list of sets. The power set is itself a set, so we should return a set of sets. But unfortunately, we can't do that. Right there. We can't return a list of sets because sets themselves are not legal elements of sets. This is a representational issue in Python. The representational issue comes from the fact that to get that efficient representation of sets, where we can do efficient indexing of sets, requires building what's called a hash table. And sets are not hashable elements for reasons you'll discover in data structures when you get to it. So we had to resort to returning a list of sets to represent the power set. Okay, question?
Okay, so in your solution, what is the vertical line?
Yes, this is the union symbol for sets. So a subset is a set.
I forgot about that.
Yeah, we did this week 2 or something. We talked about set operations. And there's union and intersection, right? Intersection is the little ampersand, and union is the pipe. I admit I have to look that up sometimes. Go ahead.
Subset a keyword?
Subset is the element, is the iterative variable in the new set. This is just a comprehension. That is a list comprehension right there. Returns a new list structure which I concatenate to the existing list structure. This new list structure is a copy of the old list structure where every element of the old list structure has the new element added to it. So this comprehension builds, for every element in U, it builds copies of those elements that incorporate the element I had just removed from the set S. When I concatenate those with all of the elements of the power set of the rest of S, I've expanded my power set by 2, those that don't include the element and the copies that do include the element. You see? It's pretty cool, right? Anybody else? Well, that's the last slide you get in CS1. So we're done in 15 minutes in, unless you have questions. So I'll open the floor for questions. Anybody? Ask me anything. Go ahead.
What do you think we should start reviewing for the final?
So it's a valid question. There's going to be a question on algorithmic runtime, surely. So we might want to review the lecture on algorithmic runtime. We didn't do that in exam 3, recall, because we focused on object-oriented coding. There will be coding questions. You will be given question of the day, like maybe nothing quite this hard, but question of the day style questions will be in there. And you can expect that those will include questions that require you to use comprehensions or set operations or write a recursive function or that kind of thing. So that will surely be on the exam. There will probably be something that is object-oriented, a little bit like maybe the last exam, but maybe not quite so long. What else have we done? Well, one simple way to do this is simple, maybe not so simple, but one thing we can look at. I don't know if you guys have watched this, but you have the index of every slide that we used, right, is here in reverse order. So as I look back over this, there may be a question on tractability, intractable, tractable, and decidable, undecidable, but it won't be prove something. It'll be like explain what this means. Something like that might be on the exam. As we walk back here, there may be a simple regular expression, nothing complicated. Things like, match a phone number. Yeah, in the back.
You said before that programs that you showed us in class were available on Canvas. Where do we access them?
Programs that we did what in class?
That you walked us through in class are available on.
Well, they're all on the videos, right? You can go back and see, and they're all indexed here. If you look, all of the question of the days or labs, when they're discussed in class, you'll see it like lab 10, and then the name of the function or the element we talk about. So for this one, you can go right back to April 13th and see the thing. Yes?
We can't see the pages tab on our icons.
I'm sorry, I can't.
We can't see the pages tab on our icons.
Can somebody here can repeat?
He said we can't see the pages tab on our icon because it's hidden from us.
Oh, there's nothing in pages. These things aren't enabled for us. These are not live indexes. If you want to see this lecture, well, let's just do this. 24.4.13, you go to UI Capture, and every lecture is there in reverse chronological order. What are we looking at, 4.13? So if you want a particular slide, you can go to that slide and find what you need, right? So the index just tells you which lecture to look for. Does that answer your question?
It actually executes a purchase.
So sorry, this pages tab, all this stuff that you see here, all this junk here, this is what an instructor sees an icon, because there's a lot of modules that you can enable or disable, and they have the eyeball with the slash. They're disabled in this class because I don't use those. Pretty much the only things you need are assignments, UI Capture, and then the files. There actually are files on the website, but they're all linked in the announcements or in the assignments, like all of the PDFs of the assignments and things are in the file space, but there's no need to access them directly. Just go to the assignment and you can access it from there. Let me just say what I mean here. So if you go to an assignment like homework 3, these files and templates, they're all available directly from the assignment. You don't have to go to the files listing. All right, so what were we doing? We were going through things that are likely to be on the exam. I don't know if I've answered that question enough or not. You want more background on what's there? I mean, we could go all the way back. It would be legitimate for me to ask you questions about set operations. I'm not likely to do it. I might ask you to write a function that uses a set operation. That I could certainly do. Okay. Certainly sorting and searching and binary search, all those things are legal, including runtime arguments about, say, binary search. That kind of stuff is legal. I don't think the exam will be 2 hours long. I imagine many of you will stay 2 hours because that's how people take exams, but I don't think it'll be substantially longer than the one that we had for midterm 3. I don't see any reason to have 2 hours worth of stuff to grade. It's just not necessary. Anybody else? Go ahead. Yeah, I always hand out the cheat sheet. Do you find this useful? Is the cheat sheet useful to you in the exam? I mean, there are things on that are not on the cheat sheet that I wish were. Right? There are some things that the cheat sheet doesn't contain, but it does have enough to sort of get most of the stuff that you need. And it is the most concise, best laid out one-pager I've ever seen for Python. So that's why I keep using it. It's done by some guy in France, and I think it's a really elegant solution. But it doesn't have everything. One thing that you might want to do in the back before the exam is pull out that cheat sheet. It's on our webpage. Go over it and ask yourself, what's not on here that I should know? And that would probably be worth doing. All right, because so things like sometimes set operations I think aren't on there, stuff like that. Anybody else? Well, did you have fun? Did you learn something? Yeah, right? I mean, you all feel somewhat confident now when you're given a problem like I can do this? Yeah? Yeah. Look, it's a skill. It takes practice, right? Who's read Freakonomics? Anybody? I loved that book when it came out. It's a little boring now, but it was good when it came out. There was a chapter in there about practice, and I think I may have mentioned before, I was a music major in college, and music majors spent a lot of time in little rooms with no windows, playing an instrument alone, right? This is what you do. And there was this sort of story in Freakonomics that said the difference between a good violinist and a professional violinist who can make a living playing the violin were hours of practice time. And I think the same thing applies to coding. This isn't something that you learn and you're just naturally good at. It's something you have to constantly practice, right? So every year I teach this class, one semester, and I don't write a lot of Python code in the other semester. So every year I have a learning curve to get back to remembering how to do stuff in Python. That's normal. You're going to go home for the summer, you're not going to write any code, and at the end of the summer it's going to be like, oh God, I got to write a program, where do I start? My advice to you would be, one of the things about remember we have the two texts, Think Python and Python for Everyone. The Think Python text is, I think, the better, easier to use reference book. It's not a great textbook. Python for Everyone has some cool chapters that we didn't cover, including one chapter where you integrate Python with SQL, or you do some more natural language, or you look at maps with Python. I would urge you, if you have time over the summer, you're looking for something to kill in your spare time, write a little Python code. Just keep your hands at it. Because when you come back in the fall, How many of you are taking discrete structures next fall? And data structures at the same time? Yeah, so you're going to be coding again. And it won't be in Python because we teach data structures in Java. But Python will remain, I hope, your go-to language for quick and dirty computation. It is mine. I do occasionally write Python code to sort of clean up and process data that I get for our research projects, where we deal with a lot of data. And so it's often not clean or badly formatted or needs to be, processed in a variety of ways. I use Python for that. So those kinds of things, you'll find Python is the most convenient vehicle, and you should just keep it up enough that you don't have that sort of where do I start feeling when you open a Python file. Anyone else? Yeah. Am I going to have date time? Oh, date time. You did it. The homeworks are legit questions to ask, but I'm not going to ask you stuff that you didn't already use in the homework, right? So, and if I say, then I'll introduce the function and say, date time now returns today's date or something, so that you don't have to. It won't be a test about did you read the manual, because that's silly, right? The manual is always going to be available to you. But the idea that representing dates and times, that there's an object that represents them, that you can do arithmetic on those options, on those objects, and get back a different type of object that represents a time interval, those concepts I think are legitimately testable. In exam 3, there was a date time question, but it wasn't anything that you hadn't seen in the homework. Anybody else? Yes?
Will the farmer have the question similar to the midterm 1, like point out the error, or just like midterm 2 and midterm 3, just write down the code?
Oh, yeah, there will be stuff that you have to write code for. So like midterm 2 and 3, where I'll give you a few lines and say write a function that does this. I often on a final will write a function with errors in it and say, here's a function that does this. Point out the 3 errors in the function and how you would correct them. That's a favorite question for me on final exams. I don't think there will be stuff like in exam 1 where here's an expression to evaluate, because by now I would expect that these would be actually quite easy because you've done a lot of Python interaction, so you'll recognize, you won't fall for the old left parentheses 1, right parentheses as a singleton tuple, right? That's the one that everybody gets wrong on exam 1. You will know now that a singleton tuple needs a comma, right? That kind of stuff. So I don't test that. Okay? Anyone else? Okay, well, then let's call it quits. It's been nice having you. I always enjoy teaching this class. I understand it's challenging for students because we move quickly and because it's a lot of work. But I hope that you recognize that the more you practice outside of class, the whole reason I give you questions of the day, because they're not worth much, is to make you write code. And the only way you're going to get better at this is if you write a lot of code. So I hope that in this class, where you have in fact written a lot of code, that you got a good head start, but that you'll continue to write. Don't forget, student evaluations are open, so you know how to do that. Yeah, in the back. Huh? That's all right. It'll come back to you. Post your questions to Piazza. I'll answer whatever backup questions I have. I didn't answer this morning, but I'll do them now. For those of you still working on homework 3, I'm in my office next week. If you have email, if you want to email or if you want to write on Piazza, I'll be answering still. Yeah, go ahead.
When are we going to get our next GS?
On Monday morning. The TAs are almost done with homework 2. As soon as those scores are loaded, I'll run the estimates and post them. It'll be on Icon, there'll be a G estimate 2 or something, and I'll post an announcement there. Okay? All right. Well, thanks for a great semester. Good luck on the exam and on finishing the homework. And hope to see you next term.